This is StarTalk.
Welcome to StarTalk All-Stars. I'm Janna Levin, and I'm your all-star host today. I'm an astrophysicist and author, but nowhere near as interesting as my co-host, the incredibly talented Matt Kirshen. Matt, welcome to New York.
Hey, thank you for welcoming me both here and to the show, and for pointing out that I'm more interesting than an astrophysicist.
And that's right, and we're going to hold you to that for the rest of the hour.
Much more interesting.
Also in the studio, we have special guest Shepard Dolman, who has a long list of accomplishments, including getting through graduate school at MIT, same year as me.
And getting here
together,
this morning.
Getting me through general relativity. Shep is an astrophysicist at the Harvard Smithsonian Center for Astrophysics and the director of the Event Horizon Telescope project. Event Horizon Telescope is a fantastic project, not yet complete, still under development. It is a telescope essentially the size of the entire Earth that is going to try to take the first real picture of a black hole. Very exciting stuff. So this is what we're going to talk about today.
It's a good day's work if we can pull it off.
It's a good day's work. So we're going to be talking about black holes, how we observe them so far, why we think they're real, and what it would mean to take a real picture of them for the first time. So Shep, thanks so much for coming, making the trip from MIT and Harvard.
Thanks for having me. It's a pleasure.
Today, we're going to delve into one of the weirdest and sort of most exciting topics in astrophysics. Everyone loves to talk about black holes, and in particularly how we observe them. But first, let's just start with, what is a black hole? Shep?
So everybody, I think...
You throw straight to Shep. I get it. I see how things are. Someone's already playing favorites. I didn't go to school with you.
You didn't
go
graduate.
back 20 years, so you just go to Shep to immediately ask about the black holes.
Yeah, you didn't graduate from MIT.
Well,
we have rings that have a beaver on them.
Really?
Yeah, the beaver ring is the MIT class ring.
The industrious engineers.
Quite appalling. Yeah, I know.
All right.
That face says it all.
Oh, because of building things. All right, that makes a lot more
We
sense.
build telescopes, we image black holes. That's what we're all
I get
about.
you.
So black holes,
So black holes, what are they?
what are they?
Well, everyone has some idea of what a black hole is, but essentially it's when gravity's run amok. It's when mass collapses in on itself to the point where gravitational runaway is inevitable. And nothing can keep matter from infalling to a singularity, to a point. And the interesting and defining thing about a black hole, and this is what we all probably know about, is that there's this membrane called the event horizon around the black hole. And that's the point outside the singularity where gravity is so strong that even light can't escape.
And
Is
that's
it an
named
actual-
after the movie.
It's the other way around, actually, but it's...
Interesting.
It's what most people think about when they think about the Event Horizon, the movie, and the spaceship that went into hell and then came back out haunted.
So the event horizon means no events that happen on the other side of that line will ever be known to you. So it separates causally, right, two parts of space.
Okay.
But
What happens in the Event
What's she
Horizon
talking
stays
about?
in the Event Horizon.
so is
will
it an
be.
actual membrane?
It's not an actual membrane, it's just a region of space-time that demarks where gravity is so strong that the escape velocity from that mass is the speed of light. So once you pass through it, you really can't get back out again.
Yeah. If you could actually stick a light pulse right at the event horizon and racing outwards at the speed of light, it wouldn't go anywhere. It would just sit there.
It
It's
would be
one of the-
frozen.
It would be, just hovering there. It's almost as though space-time's falling in like a waterfall.
So what would you see if you were actually right at that event horizon?
You would pass the light pulse and think it's traveling at the speed of light. So, but this is a good question, Matt, because you say matter is a dense, crushes under its own weight. A big enough star will crush under its own weight eventually. So is there stuff there? Like people think of a black hole as this incredibly dense object. So when I cross the event horizon, like Matt asked, is there anything there?
Usually there's nothing there.
nothing there.
Especially for
It's
a
the weirdest.
supermassive black hole, like the ones that are in the center of our galaxy or in other galaxies, you just pass right through the event horizon like it's not there. But you can't get back out again. It's one of these strange things. That's why philosophers get very dreamy when you talk to them about black holes in a way that they don't when you talk to them about stars, because world lines can go through the event horizon and you don't know what happens.
What's a world
inside
line?
there.
What's a world line, Chad?
A world line is where you are following space and time on your own trajectory. And I go from this point to that point, from point A to point B. But if point B is inside the event horizon, you can't get back out again. So you can't tell your friends where you are or how you got there.
Yeah, you know how Google Maps plots your spatial path? They should do a space-time diagram, right? So the world line's your path through space and through time.
But sometimes it gets it wrong and it picks like the wrong Massachusetts or whatever, and then it says you need to take a boat
and then you need to take a left turn,
Right.
and then a boat.
And then you'll never escape. All right, I get it.
But the thing about the GPS units is they do actually have to correct for relativity to get your location right on the map. So our clocks run a little bit slower here on Earth than they do, say, at the satellites. And so they have to correct for that time difference, the fact that our clocks are running slower, that we're aging slightly more slowly, in order to locate you properly on the Earth. So,
And I think that's hugely interesting, right? Because Einstein developed this theory of general relativity in 1915, over 101 years ago. And sometimes I imagine going back and talking to Einstein and saying, "Here, Professor Einstein, 100 years from now."
Don't have to put on the voice.
I do have to put on the voice. If I don't put on the voice, it doesn't sound good, right? So you go back in time and you say to Einstein,
do you talk to everyone in the accents that they have? Are you going to start speaking British to Matt?
Don't get me started, right? But you talk to Einstein, you would say, 100 years from now, corrections that you discovered will enable me with my phone to take downlinks from a constellation of satellites around the Earth and pinpoint my location to anywhere on the Earth. And of course, he'd be very excited and he would say, "What's a phone?"
Right.
Because our technology has gone so far beyond what Einstein had that the first thing he'd be interested in is, well, what's a phone? And
I thought he refused to memorize his phone number because he said, why would I memorize anything I could look up? Like, why clutter your mind?
When you're as bright as Einstein, you can get away with a lot of stuff.
Yeah, well, he also said, when I was a student, I was no Einstein. So, how do we know that
I
these
was
crazy...
also no Einstein as a student, so does that make us kind of on a par?
That's right. It works in both directions.
Also, I don't know Einstein's phone number, so we're kind of exactly the same person.
Did he have a phone number?
Intellectually, clearly very similar.
Yeah.
Wouldn't he have had a phone number?
Maybe.
So maybe this is one of those apocryphal stories that I'm propagating without having properly looked into the
He had an
history.
assistant that just took care of all that for him. That's what I think.
So black holes, Einstein understood the mathematical solution, but he wasn't sure that they were real. In fact, he sort of thought nature would protect us from their formation. I mean, after all, I can't crush this desk very easily. It's very, very hard to do. I mean, it's hard to fold a piece of paper more than, what's the number? 11 times or something like that.
The 11th.
It starts to really fight. So he believed quite sensibly that nature would not allow something to collapse all the way to a black hole. And there were decades between that time, 1916, this guy in the trenches, an infantry soldier on the Russian front, is calculating ballistic trajectories and writing to Einstein, naturally. Mm-hmm. And he wrote down the first solution for a black hole. Do you know when it got its name, the black hole? Do you know who gave it its name?
Peebles gave it.
It was Wheeler, I think.
Wheeler.
Also
Wheeler,
a Princeton guy.
I
Yeah,
don't know what
apparently
year that was.
It was 1967, and I'm not going to tell you why I know the year, but I haven't.
It's the year I was born.
It's the year Shep was born. And he was tired of saying end state of complete gravitational collapse, apparently, so someone from the audience shouted, "How about black hole?" And the name stuck. That's 50 years, right? 50 years it took for people to really start to believe that black holes were real. So why do we believe they're real now?
Well, the way I think about it is that for a long time people didn't think that anything could be much denser than water, right? So if you take our sun, the average density of the sun is not too much more than water given its volume. Like you could fill the whole volume of the sun with water, it would weigh about what the sun weighs. And it wasn't until people found white dwarfs, which are very dense end states of stars, like cinders of stars. It'll be the end state of our sun, for example, and neutron stars, that people began to really think that matter could be compressed to extreme density.
So just to be clear, this is scientists who didn't think things could be denser than water, not just like people in the pub.
Right.
Yeah, well,
People have theories. Like I remember my friend Jordan telling me when we were like 8 that the way we could travel faster than light is, I don't know if you saw the end of Jaws, but like the way the canister of like exploded in the shark's mouth was so powerful, and he's like, that's as big an explosion as you can get, and that'll get us like faster than the speed of light. And it turns out Jordan was wrong.
Yeah.
But
Jordan's one of those people apparently who write me those, their theories of everything.
you get those? I bet you do. Both scientists
I'm
get
going to search for the name Jordan
Yeah.
in my crazy folder.
you always get these letters that say Einstein got it wrong by a minus sign, and here's why.
Right.
Yeah.
Although he did have a minus sign error in some of his first papers. Yeah, but not in relativity. I mean, he made mistakes. He wasn't really afraid of that. I mean, this stuff is, it's not written on a tablet somewhere. It takes some trial and error. But sorry, was there more to Jordan's theory?
No, that was mostly it. I mean, like,
I think we should just call it Jordan's theory.
basically, anything that can explode a shark is going to be pretty powerful.
Well, actually, it's quite amazing. They really needed to understand the nuclear physics that goes into the bomb technology before they were sophisticated enough in their understanding of small-scale matter forces to realize that a black hole would form. So all these guys really did work on the bomb. But on that happy note, we're switching to cosmic queries. Matt, what do you got for us?
So on that note, here's a question from Victor Furtenbach on Facebook, who says, from Stockholm, Sweden as well. Is it possible to kill or destroy a black hole?
Wow.
Is it alive?
A black hole hunt. I really like that.
Like wood putting a compressed air canister in the black hole's mouth and then shooting it from a boat.
I think a shark could easily.
Right. Like how big
Devour
would
a
the
black
shark
hole.
have to be to eat a black hole?
I guess it depends on what you mean by destroy.
Yeah, well, black holes will evaporate by themselves if just left to their own devices, right? And that's because of something called Hawking radiation. So the boundary of the black hole, this event horizon, is a turbulent place, and you can get particle and pair production, right? And one particle will go into the black hole and one will go out of the black hole. And from a distance, it looks like the black hole is giving off particles, slowly evaporating. And over billions of years, a stellar mass black hole can just vanish, right? So that's one way to get rid of a black hole, just leave it alone
wait
somewhere.
for a very long time.
It's
Ignore
a very
it.
long time
Ignore
because
it.
right now the light left over from the Big Bang is hotter than all the astrophysical black holes we think we know of, so that the black holes right now are absorbing the light right from the Big Bang. They're not emitting it yet. But in a long time, everything will fall into black holes, and then all those black holes will evaporate.
This is like like if this black hole is currently terrorizing a seaside town, like this is not the approach that you want.
Yeah, that would not be a good, protective measure. Yeah, that wouldn't work.
Yeah, but also a shark-sized black hole a shark-massed black hole would be really tiny.
Can you make
Right.
that? Can you have a black hole that's that size?
Oh, sure. So if you had a black hole that was the mass of an asteroid, for example, let's say 100 trillion kilograms, it's a good-sized asteroid, it would be smaller than an atom. So it wouldn't terrorize the town. It would just drop right to the center of the Earth because there'd be no support for it.
Well, we don't actually know how to force an asteroid to become a black hole, but there was...
By direct pressure.
You apply, right,
a job.
more. But in the Large Hadron Collider, people were afraid that by smashing particles together, one of the byproducts was going to be subatomic-sized black holes. And so people did try to take an injunction against turning on the Large Hadron Collider.
Now, I remember that being a thing. Did any micro black holes actually get created? And if so, what happens?
Awesome, no.
Like, if one were to
Clearly.
happen...
Thank God.
Clearly we're safe.
Okay.
No,
So if one were to happen, it would actually do bad things. Like, even if it is...
It wouldn't, actually. So physicists just are never willing to say never. They're only willing to say it's very, very improbable.
Right.
So the argument was black holes could be made, depending on whether there were extra spatial dimensions and what gravity is really like at higher energies. But if they were made, they actually evaporate through the process Shep's describing much faster than big black holes. The smaller the black hole, the faster they evaporate. So the idea was they would just be gone in a flash. They would be like
They
an
burn brightly.
explosion.
They're tiny and they burn brightly.
Yeah. At least that's the theory.
The other thing, that people should feel safe about is that nature has already done this experiment for us. So people worry about CERN and the Large Hadron Collider slamming particles together to make a little black hole. But cosmic rays hit the Earth all the time, and they're hugely high energy. They're higher energy than you can make in the LHC. So they're slamming into the Earth all the time, and they haven't made a black hole yet that devoured the Earth. Maybe they made a black hole, but remember, black holes have these tiny little mouths, right? They're like huge animals, but with a tiny little mouth, right?
Right.
And so it's very difficult for them to eat.
I like that you're keeping everything in shark terms, and I really appreciate that.
Like the hummingbird of the exotic object world.
So do we have some more cosmic queries? Do we want to try another one?
So again, and I think this question might turn out to be slightly off in terms of the way it's phrased, but Hunts105 on Instagram. I don't know how you ask a question on Instagram. I don't know whether this is just done by posing for a picture that conveys this question.
What about holding up a cardboard sign?
Yeah, right. Oh, maybe. But Hunter from the United States says, how close would a black hole have to be in order to see it with the unaided eye?
The unaided eye.
You'd have to see the shadow cast, because that's all there is to see.
Yeah, so one of the mysteries of black holes, maybe we'll get to this later, but this is the perfect time, is that by definition you can't see them. By definition, all the action happens within the event horizon. Once things fall through, even light, you can't see it. So why are black holes actually some of the brightest things we see in the sky? That's because all the gas and dust that's being attracted to the black hole is trying to fit into this impossibly small volume. And just as when you rub your hands together, they get hot, the friction of all that gas and dust madly trying to get into this teeny little volume heats everything up to hundreds of billions of degrees.
So what you're seeing is everything clamoring to get into the black hole rather than the actual black hole itself.
Yes.
It's like,
You're seeing like the line outside the nightclub rather than what's, like, something's happening inside there and it's pretty special, but all you can see is like this big exciting line outside.
Yeah, and the bouncer is kind of like the heat, keeping everybody out.
Right.
Right, but then you think, right, maybe it's all hype.
Right.
So what Shep wants to do is take an actual picture of the shadow. So that's something amazing. But to see the shadow means there has to be something bright behind it. So if the black hole is just against a dark sky, there's no hope of seeing it, even unaided. But if it was had the Milky Way galaxy shining behind it, you would see a sort of lensed image of the Milky Way, and you would see the shadow. So it's an interesting question. How close would it have to be? So a black hole the size of the sun is about 6 kilometers across. So how close would 6 kilometers have to be, Shep, do you think, to be able to see it? In the case of my eyes, like right here.
Yeah, it would be like within the solar system. Like, so if you're out in the orbit of Pluto, for example, and you look back to the sun, you can't even see that, right?
Right.
So you'd have to be well within the orbit of Mercury, I would imagine, to even see this kind of thing.
Well, so Sebastian Dubus on Facebook says, where is the closest black hole and could we send something to orbit around it?
Well, that's a great question. We often joke that the best way to study a black hole is to send an undergraduate with a laser pointer to the nearest black hole and throw them in, right? And then as they go in, the laser, of course, would be Doppler shifted, and you'd see the dynamics.
They get extra credit for that, though, right?
They totally pass the course.
Okay.
Yeah.
That's going to look really good on the resume.
Well, the nearest one is it's just like a few tens of light years away, I think. Like Cygnus
right?
X1, that's one.
I thought it was 6,000 light years away. Oh, fact checkers.
Yeah,
Well, is there a black hole at the center of the Milky Way?
There's absolutely
Yes.
a black hole at the
And
center of the
that's
Milky Way.
further away than the nearest black hole.
Yeah, that's about 25,000 light years away.
Oh, okay, so the nearest black hole, is that also part of the Milky Way, or how does it?
Yes.
Okay.
Yeah, so there's 100 billion stars in the Milky Way, and about a million of them, what did I say, 100 billion? About 1 billion of them, actually, will one day become black holes. It doesn't mean that they all are now. So there's a lot of black holes just speckled around the galaxy, a lot.
No, we may talk about this later, but the black hole at the center of our galaxy is one of the only ones that we can hope to resolve with any kind of astronomical instrument. So the kind of telescope that Janna was referring to before, the Event Horizon Telescope, can just make out the 4 million solar mass black hole in the center of our galaxy.
This is a perfect place to break, because we're going to come back to talk about the Event Horizon Telescope and how it's going to resolve that shadow and the excitement of that project. So we're going to take a short break, but stick around so we can talk more with Shep and Matt about Event Horizon Telescope on StarTalk All-Stars. Welcome back to StarTalk All-Stars as we continue to talk about black holes and Event Horizon Telescope. I'm your host, Janna Levin, and I'm very excited to have my wonderful comedic co-host, Matt Kirshen.
Hey, Janna.
Hey, Matt. Long time no see.
Been a while.
Been a few seconds. And our science guest, Shep Doleman. Shep is the leader of the Event Horizon Telescope project. So tell me a little bit more about Event Horizon Telescope.
So the Event Horizon Telescope is a project dedicated to the notion that we can see something that we've always been taught is unseeable, right? So everybody knows that a black hole is something that absorbs light, matter, nothing can come out from the event horizon once it's gone into the event horizon. But because all the gas and dust is heated up and you get this effective three-dimensional flashlight all around the black hole, illuminating it from all angles, you can see its shadow or the silhouette that it casts against all that hot gas.
So what about Interstellar? Do you know how in Interstellar they show the disk around the black hole, but you can kind of see it above and below? Do you think that was a pretty accurate portrayal?
I think that's very accurate.
It was very
right?
accurate.
So because it turns out that just like water going down the bathtub drain, everything kind of falls into this pancake shape that's swirling around the black hole.
It makes like a
Mean that
disk.
Black holes spin the other way around in Australia.
That is not true, actually. Although toilets do not also spin that way
Do
in
not?
Australia.
I was just in Australia. I should have checked.
Yeah, it's one of the great experiments of our time, looking at toilet bowls. Astronomers spend a lot of time looking at toilet bowls.
Astronomers spend all kinds of time looking at things.
But the point that Janna is talking about is quite true. There is no behind of a black hole, right? So that came out wrong, didn't it? Anything that's behind the black hole, by definition, gets bent up and around. So the light rays from on the other side of the black hole get bent up and around. So you have this pancake object, and you're seeing the rear side of it flipped up.
Yeah, I always stole this line from you, Shep. You once said you can't hide behind a black hole. And it's actually a great description. You're crouching down behind the black hole, and they can see you.
Exactly.
And then if you step one step too close, you're in the black hole. Like, that was a bad game.
You're gone forever.
I shouldn't have done that.
I should have paid attention in astrophysics class.
Rosie Reeds on Instagram is asking, what is the telescope made of?
Oh, what a great question. So first of all, black holes are extremely small. They're the smallest objects theorized by Einstein's gravitational theory. And so to see them, you need a large telescope. So the larger the telescope, the smaller the object you can see on the sky. So to do this, we take radio dishes all around the globe, and we synchronize them with atomic clocks. We point them all at the same time. It's kind of incredible when you think about it, but they swivel at the same moment, look at the black hole, take radio wave data from the outside of the event horizon of this black hole, and they record it on hard disk drives. We essentially freeze the light everywhere around the globe, and we bring them all back to a specialized supercomputer that compares them all. It operates exactly the same way that an optical mirror does for an optical telescope. So for an optical telescope, the light rays hit this perfect paraboloidal shape, and they focus it all to a point where your camera sits. All the light is focused to a point. In the Event Horizon Telescope, we replay all of these recordings that we've made all around the Earth, and we adjust the timing of them to make it seem as though there is this huge dish the size of the Earth. And then we synthesize this focal point, and that's where we make the image.
So the whole Earth is a telescope.
Well, telescopes around the Earth form the telescope.
So it makes this like giant machine. So how big? I mean, I remember this comparison. If you resolved the shadow of the black hole from the supermassive black hole at the center of our galaxy, which is how big is it again?
It weighs about 4 million times what our sun does.
And about how big across is it?
Well, on the sky, it measures about 10 micro arc seconds, and the shadow would be about 50 micro arc seconds. This is the same as trying to observe your favorite citrus fruit on the moon. So it's a tangelo, grapefruit, a pomelo.
This is going to sound weird, but I don't actually have a favorite citrus fruit.
It does sound weird, and I'm disappointed.
I know, and
I've
been mocked for it in the past because it comes up a lot. And people are always like, what is your favorite? I'm like, I just like them all the same. And then
you have to choose, Matt. You have to choose.
I sound like one of those parents who you can't love all of your children the same. Like, I just don't have a favorite amongst.
When you next go to the moon, I want you to put one that you chose on the surface of the moon, and we will try to resolve it with Event Horizon Telescope for gags.
I can't believe I'm on the show with someone that doesn't have a favorite citrus fruit. It's kind of awkward.
No, I know.
I heard it's like resolving a quarter on the moon. Is that the same?
No, almost. So it would be a citrus fruit on the moon.
Citrus fruit is bigger than a quarter.
Or if you were in New York, as we are now,
Yeah.
and your friend was in Los Angeles holding a quarter, it would be equivalent to reading the date on that quarter.
And that's what you guys are trying to do.
That's what we are trying to do. So
How much of being a professional scientist is coming up with different size analogies? Because that does seem like a lot of the job of it would be like if Pluto were a baseball and your hand was Alpha Centauri and your dad was throwing Pluto from. It just seems like there's a lot of that. That's what we are. We're idiots.
I feel that
he
I'm
has
not
a real
living up
future
to
in
it.
this business.
Put this in terms of swimming pools and whales and fruit. That's how I need to understand science.
Like hamsters, habit trails.
Okay, but this black hole, which is 4 million times the mass of the sun, probably fits in about 3 sun widths. Does that sound like about right? I'm not sure.
No. It's probably about the event horizon would be about a third the orbit of Mercury.
Oh, so that's bigger.
It's actually because it's 4 million times
Oh, yeah.
that
So
6 kilometer figure that you gave
Okay,
before.
so
It's quite large.
Yeah, so it's quite large, but it's 26,000 light years away.
Exactly. So as I said, black holes, they toss stars around like planets, these supermassive ones. They're hugely dynamically important. But the largest one that we know of that's close to us is 25,000 light years away. So it's not going to hurt us. We're not in any danger.
Well, we are falling into it, just really slowly.
Very, very slowly.
Much worse things are going to happen to us in the next 10 years.
Well, and I can think of several.
But not to get off topic. So this is the biggest black hole in our galaxy. It's at the center of our galaxy, and we think that there are black holes this big in all the galaxies, more or less. Do we have any aspiration for observing the shadow, of taking a picture of the shadow of another black hole, a supermassive black hole in another galaxy?
Yeah, so it turns out there's one other wonderful candidate for doing this. So the number one target for us is the supermassive black hole in the center of the Milky Way galaxy.
Sag A star.
Which is called Sagittarius A star in the constellation Sagittarius. And the other one is in the Virgo A galaxy. And that weighs 6 billion times what our sun does.
So it's
a
big.
Real monster. It's a huge monster.
So it's 1,000 times, more than 1,000 times bigger.
Yeah, it's about 1,500 times.
It would be
It's still
1,000
part of the
times.
Milky Way.
No. It's a different galaxy, a whole different
okay.
galaxy.
And so the only reason why we have any hope of resolving that is because it's so much bigger, even though it's much further away. How much further away
it's proportional. So it's about 1,500 times more massive. But it's also about 1,500 times farther away.
So it works
looks
out.
about the same on the sky. So a telescope with the same magnifying power would see them both about the same size.
So you're basically building a telescope the size of the Earth to take the picture of two things.
Yeah, but
in the
what two
entire
things they are?
universe.
Like, I like to say it this way: if I were to be trapped on a desert island with two targets, these would be the two targets, right? So we have one that is kind of a Rosetta Stone, if you will, or it's an exemplar of most of the supermassive black holes in the universe. They're nondescript in smaller galaxies. We wouldn't see them if they were
Why
very
can't
far
we
away.
see our black hole?
It's just not bright.
It's not bright because it's just not taking anything down right now?
Yeah, it's on a starvation diet. It's kind of eating with a teaspoon, and so it's not the gas around it is hot, but it's not enough to really be seen from very, very far away. Whereas the Virgo A, the supermassive black hole, is much, much brighter, and that's driving a jet of relativistic particles from its north and south pole that's literally piercing the entire galaxy.
Now, is that because
Virgo
we're
A.
seeing it in the past, when it was more active?
Well,
Is it not that far away?
it's about 17 megaparsecs away, 17 million
So it's
light years
not
away.
really old enough.
So it's not too old. We're probably seeing it as it's eating, as it's driving these jets from its north and south pole through the galaxy.
So in the past, was our black hole at the center of our galaxy bright?
Oh, almost definitely.
So there's probably some alien civilization on the other side of the universe where the light's taking billions of years to get there that thinks that our black hole is like a quasar.
How do you think
something
their
like
version
that.
of this show is going?
It couldn't be going better.
It could not be going better. This is the best universe in which this show is going the best.
Well, so
I feel like Trump. It's the best.
it's huge.
It's huge and it's the best.
Well, what I'll say very briefly on this is that about 300 light years from the center of the galaxy, they see these wisps of X-ray light. And they think that what causes that is that 300 years ago there was a burst of activity in the center of our galaxy, and the shock wave has reached the clouds that bound that area, and it's fluorescing.
So speaking of which, we're seeing the black hole 25,000 years ago, as it was then. So wasn't there this excitement for a while that a cloud was about to be torn apart by the black hole? G2, gas cloud 2. And people watched it for how long? Were they watching this gas cloud?
Yeah, so there was a cloud of gas that they thought was about 3 times the mass of Earth, and it was falling into the black hole. And they knew it was falling in because it began to be tidally stretched. So the front part of the cloud was feeling more gravity than the rear part of the cloud is being stretched.
So it was like streaming out.
Right.
Right?
So it's like the exciting bit when you're watching the water drain out of the bath, like when it just suddenly starts to go
It's the only fun part of that watch. Yeah.
Before you hit the towel. But in any event, people thought there was going to be fireworks. There were going to be fireworks, and we haven't seen anything. It's been the biggest dud
Right.
ever.
So what do you think happened?
Well,
Did it just not fall in?
A lot of it depends on how you engage the black hole. So if the black hole is spinning this way and you're coming in counter to that rotation, you could get a lot of fireworks. But if it's spinning in the same direction as you, you'd just be sucked along with it.
Yeah.
And it might take a long time for the gas that you're contributing to the black hole to find its way all the way to the event horizon where it would light up.
Yeah, let's be clear. If I were to fall across the supermassive black hole in the center of the galaxy, I would not be torn to shreds. I would just drift across, right?
That's
Just drift across happily because I am wee compared to the size of the event horizon. Matt, what do we got?
So Carl West on Instagram is saying, will this telescope be studying the effects of Hawking radiation?
Probably not. So
Suck it, Kyle.
no, Kyle. It's a great question, Kyle. I'm going to protect Kyle from Matt here. It's a great question. We know that Hawking radiation exists, but the Event Horizon Telescope is going to see this outline. And Hawking radiation is not likely to affect that outline. There are some cases in which it might. There are some quantum effects that might affect the shadow size, and that's an active area of debate right now. But Hawking radiation itself is something that happens over very long periods of time. And so we probably wouldn't see that dynamically affect the shadow.
You know, I should point out that we are getting cosmic queries from our audience through social media. So next time, tune in and send your questions ahead of time, and we may or may not actually get to them.
Yeah, so Blair Jackson on Facebook asks, could the Big Bang be the birth of a black hole? And are we all living within a black hole?
I almost think it would be the other way around. People have speculated that the black hole could harbor a Big Bang inside. So the black hole is much bigger on the inside than it is on the outside. It could be as big as a universe on the inside. It's like Doctor Who's TARDIS. You know, you go in a small little red box, but inside is an enormous lab. So you fall into the black hole and you think you've got a microsecond before you hit the singularity, but your quantum bits get blown out into a Big Bang.
So the second part of that question, where Blair says, are we all living within a black hole? We could be, like this could be the...
When we look back at the Big Bang, we might be looking back at the singularity inside a black hole. In that sense, it's not really inside, but in that sense, yeah, although most people don't really take that speculation very seriously, it's intriguing to contemplate. I always find myself kind of going back to that suggestion. No matter how many times people tell me why it's faulty or what the problems are, there's something appealing about that.
Well, there's something interesting about the singularity being in every direction, right? So the Big Bang is everywhere you look. Right? So in that sense, it is not unlike a black hole.
Yeah, the singularity of the Big Bang and the singularity of a black hole are so similar that people have just kind of tried to artificially sew them together like a quilt and see if it matches.
On that same note, Dale Cheslett-Rose on Facebook says, if sound needs air to pass through, did the Big Bang actually make a noise?
Well, we're going to talk about this in a gravitational wave episode. In a sense, the Big Bang probably did make a bang in the sense that it rang the drum of space-time, where you imagine the three-dimensional drum of space-time is ringing in response to this kind of chaotic event. So in that sense, it might have, made, in a sense, a noise that if we could record the shape of the ringing drum, we would interpret a sound.
Okay.
Even in the absence of air.
So
although there
black
is
hole
stuff.
eats, it changes its shape slightly, and that changes the gravitational waves that it's emitting.
And also around the black hole, the accretion disk can support sound waves, can't it? So this disk that you were describing of all this material falling in around the black hole and flattening it out, it can have a sound wave through that material.
As long as you think of sound waves not as being something we can hear with our eardrum, but as being waves mediated by some kind of medium, like gas or dust or something.
Or space-time.
You sound like a Brooklyn DJ.
That
just
chef.
different ways to interpret sounds. You just it's just not.
What's your
it's
handle?
Not just something you can appreciate through your ears, but it's also just about just the feel of the space time. Anyway, here's my disc. Important question. Also coming from Nick Spinell on Facebook, and I don't know which of you two is going to be the best to answer this. Can we send Hillary and Trump to a black hole?
Or they might annihilate each other before they got there. That might be true. Well, here's the interesting thing about black holes. No matter how you feed them, they all look the same. So you can take a black hole and you can fill it full of Hello Kitty dolls. You can put old rusty refrigerators in it. You could throw Donald Trump into it. You could throw Hillary Clinton into it. And after it's done settling down, you would have no idea what went into it.
This is kind of deep. There is no way to tell the difference between a black hole made by crushing Donald Trump to a point and that made by crushing Hillary Clinton to a point.
All politicians are the same, man. That's
because
what
all politicians are the same.
It's just that Massachusetts would vote for one and not the other. That's the only way you can tell.
So do we have a last cosmic query in our final few seconds? Our last minute? At least here on Earth?
Let me see.
Take one from the International Space Station. It'll last longer.
This is there a correlation between the law of conservation of energy and the fact that time stops at the speed of light? Does this have to do with light having no mass because it is pure energy? Says Jacob Seymour on Facebook.
I have to read that again.
Yeah. Okay, so I'm going to try this. Anything that has no mass will travel at the speed of light. Anything. So we think that there might be subatomic particles that, like neutrinos, some neutrinos, which might also have no mass, and they would have to travel also at the speed of light. And their energy can be converted to mc squared equals mc squared energy, but it is a pure energy of kinetic energy. One way to think of E equals mc squared, which I've struck upon lately, which I really like, is to think of it as your kinetic energy through time, the amount of energy you transport by your motion through time. So if we were to draw those space-time diagrams, when you're running in your Google Maps, you know you have some energy as you move through New York City, but you haven't plotted your energy as you move through time. And that's E equals mc squared energy. And on that note, unfortunately, we have to take a quick break, but we'll be right back with StarTalk All-Stars so we can answer some more of your cosmic queries with Shep Doleman and Matt Kirshen. Stick around. Welcome back to StarTalk All-Stars, where the topic of the day is black holes, how they work, and how we hope to take a picture of our first black hole. I can't think of two better people to talk to on this topic than Shep Doleman, an astrophysicist and leader of the Event Horizon Telescope Project, and the very funny Matt Kirshen, who also hosts Probably Science. Probably Not Science?
It's just probably science. That's what it is.
Is it probably science?
We didn't need the word not in there. The word not simplified by the probably.
I'm Janna Levin, your all-star host for today, and I want to pick up with Shep on the Event Horizon Telescope because this is still a project under development. You're talking about we will observe, we hope to observe, and there are these two objects. So first of all, when do you expect to start making these first pictures of the black hole at the center of our galaxy, and why are you going to do this?
Good questions. So we started off on the Event Horizon Telescope project by linking 3 radio telescopes around the world together in Hawaii, in Arizona, and California. And the first thing we realized was that the supermassive black hole in the center of our galaxy, Sagittarius A star, had a size that was predicted by this shadow feature. So 100 years ago, Einstein came up with this idea that a black hole would cast a shadow, and we saw exactly that size. And that really got us excited, right? Because with only 3 telescopes, all we can do is tell the size of the black hole. Now we want to build instrumentation and put it at all the other telescopes that we can around the world to fill in this Earth-sized telescope, and then we can make an image. Because the whole reason for doing this is to look at the size and shape of that shadow, predicted again by Einstein, to test whether Einstein's theories break down at the edge of a black hole, and also to study the dynamics of matter around the black hole.
Now, will you really be looking all the way at the event horizon? I mean, after all, light can orbit a black hole, but, you know, to actually get all the way to the shadow, are you really seeing the event horizon, or are you seeing a little bit further out?
So you wind up seeing a little bit further out. There's something called the last photon orbit. And light, as fast as it goes, also is constrained to orbit around the black hole.
Yes.
That's how deformed the space-time is. It's a crazy, crazy place.
You could stand there with a flashlight and look at the back of your head.
Or you could illuminate the back of your head.
Right,
Yeah.
and then it would bounce off your head and you'd see it in front of you.
So if you were having a bad hair day, you would know it immediately, basically.
Because that's what you're worried about when you're, you know, right outside a black hole.
Yeah, wouldn't your hair automatically become bad just because it's kind of been sucked towards it? Like how much of it would...
You would see how bad it was.
You think your hair feels gravity more strongly than the rest of you?
That's the spaghettification of your hair. As it
Right.
Hair might sort
goes
of be
in.
left behind.
Would it kind of be more frizzy, or would it be more like high volume? Like what kind of shampoo would you need to use?
There
around
might
a
be
black hole?
special black hole products. I think we've just started. Somebody right now is scratching out a memo at their pharmaceutical company.
Just something else for women to be upset and worried about.
Right. More ways to oppress women.
Like what would happen to your limbs? Would you, like, would cellulite be changed near a black hole? How we...
Matt, you're fired.
Okay, I was going to endorse the hair care products, but I'm not going to touch that one.
So you are making your first observations when?
Right. So from these 3 telescopes and these humble beginnings, a global international consortium has formed. And we are now instrumenting telescopes around the world. So in Chile, even the South Pole, in France and Spain and so forth, in addition to the ones we already have. And the new observations are occurring in the spring of 2017, under a year from now. That's when we light up most of the array. That'll be our first shot at taking the first image of a black hole.
Do you think that's going to be a successful shot?
Of course I do. I would be getting up every morning.
Well, a lot of times, these
Sure.
experiments take decades, and the first shot's not expected to be successful, and you're thinking 10 years down the line, we'll refine enough to really nail it. But you think as early as spring, you're going to have an actual picture.
Well, we are eternal optimists, and even experiments that are long shots are always assumed to perhaps give a good result, if not light the way to future innovations that make inevitable success, a reality. So we are really focused on success in spring of 2017. At the same time, nature is nature. We have no idea what we're going to see.
Nature doesn't always comply.
It does not always comply, and we may fall flat on our face, but the idea is that we get up and we...
So is this a done deal? The consortium, the international collaboration is on board, and this is definitely going to happen?
Absolutely. So we have time on some of the biggest apertures, some of the biggest telescopes around the world. And we have these systems that are going to freeze the light at all of these telescopes at unprecedented rates.
I'm rooting for you, Shep. I'm rooting for you.
Is there ever a risk that, when you're setting up these huge telescopes, you'll see something you didn't plan to see, like
Matt waving.
Yeah, or like a neighbor doing a murder or something like that. Just I know. I wasn't expecting this, but I guess I'm gonna have to report this now.
A quarter on the moon is like a freckle on the neighbor's.
Yeah.
Yeah.
Oh yeah. So the we could. This could be like a Milky Way CSI episode or something like that, like murder at the galactic center. Well, so let me just say that we think we know what we're going to see, but nobody would be happier than most of the people in the consortium if we saw something unexpected. That would be hugely interesting. And the way I like to put it is that we'll perhaps be able to test Einstein's theory, but it's never wise to bet against Einstein. But if we see something crazy, if the size of the shadow is not what Einstein would have predicted, given the mass of that black hole, we will be really scratching our heads, thinking about alternative forms of gravity, or thinking about objects even more exotic than a black hole.
So would that mean that the whole theory of general relativity is wrong and needs to be supplanted?
Well, we know, Janna, that GR cannot be complete, right? Because at the center of the black hole, where everything is crushed to a point, the singularity, GR has to come into accord with quantum mechanics. And nobody, not even Einstein, ever found a way to do that. So we know GR is complete. The just question is how close do we have to get to the singularity before it becomes evident?
Right.
It could be at the event horizon. There could be manifestations of this deep mystery at the event horizon that the Event Horizon Telescope could, image.
So there, you mentioned quantum phenomenon, the Hawking radiation, which happens at the event horizon. So quantum fluctuation in empty space gets stolen by the black hole, and the other particle radiates, and to an observer far away, it looks like the black hole's actually emitting radiation. Is that something you think you could probe with this telescope?
Well, we can't see the Hawking radiation itself, because that's going to be higher energy particles. We know that something strange is happening at the event horizon, right? There's this thing called the information paradox, right? So if you throw an encyclopedia into the black hole, what happens to the information in that encyclopedia?
It's I know this one. It's planted by Wikipedia that everyone now uses, and you free up a bookshelf that can be used for photos and that kind of thing.
It's a real time saver.
Yeah.
These black holes. So it turns out that information has to go somewhere. Either the Hawking radiation has to encode it as it evaporates, or it gets frozen onto the surface. A lot of different theories, and in some of those, the quantum states inside the black hole may be in communication with the exterior of the black hole. And in that case, you could wind up with different orbits of photons around the black hole, and the shadow would look different. Now, you don't know exactly how different it might look, but there are ways to think about it from that framework.
Now, it's also possible that we just couldn't see any effect, but there's still something going on. But it's just too difficult to imprint it in such a macroscopic object.
Yeah, I make it sound easy. It's usually difficult what we're doing.
You make it look easy, Shep.
You do make it
Well
look
done.
easy.
I'm proud of you. Okay.
So if people at home want to build their own one of your telescopes, well, how should they go about it?
They should not, because we don't want any competition.
Don't do this at home, folks.
It's quite difficult, and I would say that the only way that we're able to think about doing it is because we have a global team of exceptionally talented collaborators that all make it happen.
So sometimes you have to kind of sublimate your own ego, right, to be part of this bigger team. It's
What
not
ego?
the lone pioneer.
No, it's really a global effort. It really is, and it's a real privilege to work with all these people.
Yeah, we're excited for spring. spring 2017?
Spring 2017.
Okay, stay tuned, people. We hope this show airs before then.
We'll have T-shirts by then.
I think it's time for the Cosmic Queries lightning round. I think I'm supposed to ding this bell.
Ding away, Janna.
I'm not very good at taking instructions. I think that's what I'm supposed to do. What do we got, Matt?
All right, from Sean Rasmussen, who's a Patreon patron, and I think you've sort of touched on this already. Hi, Dr. Levin. Why is it that general relativity, the theory of the large, and quantum mechanics, the theory of the small, cannot be reconciled as one theory of everything? If I'm not mistaken, Dr. Tyson described general relativity as being a mathematical shortcut on a larger scale, but could these two be unified with the new discovery of gravitational waves, or say a graviton? Thanks for the show! That's in like caps and like a couple of exclamation points. So like really wants to know.
Let's hope you got the accent right.
Yeah.
Well, this is a really important question. I mean, this is what all theoretical physicists pine for, is a resolution of the theory of gravity with the theory of quantum mechanics. So the large theory of the universe on the large scale and the theory of the universe on the small scale. They're very hard to put together. Even if I went through kind of a standard program, this is what I always do when I try to quantize a model of the universe, it doesn't really work with gravity because gravity is so nonlinear. Right? This is not, the effects feed back onto themselves in these very complex mathematical ways that we don't know how to control. So literally, we just don't know how to write it down. It doesn't mean it doesn't exist in reality, but we just don't know how to mathematically write it down. Our tools fail us. And so many people have tried just to find better tools, but it might be the case that they're actually not reconcilable in nature, that gravity in some sense, isn't a fundamental force. So, when I say the temperature in this room is, it's warm in this room, temperature isn't an actual quantity that belongs to anything. It's the collective behavior of group motions of small things. Gravity might be like that. It might be the collective behavior of quantum entanglement and phenomena like that. And that when we look small enough, we realize gravity's not really a thing at all. It's something, an illusion that only emerges on large scales. I mean, this stuff's really interesting. We love not knowing the answers, right? That's why we have jobs. That's why we have something to do.
So we build telescopes.
Yeah.
All right. Travis Sievert on Facebook. Travis Sievert on Facebook says, how do black holes affect time? Presumably there are sharp gravitational gradients in and around a black hole. If so, how do these affect the resulting temporal distribution of matter? Thank you.
Oh, that's very interesting. So, well, you mentioned Interstellar before. So in Interstellar, they had this moment when people went close to the black hole, and every hour they spent down there was 20 years outside. That's a real thing, right? So time really does slow down close to the black hole, and they spent time down there, and they came back, and everybody was 20 years older. So there are time gradients near a black hole, and they do affect the dynamics. And when we think about matter and light orbiting the black hole, we have to take those into account.
I'm dinging on Chet.
I wish I had one of those.
We're supposed to go more rapidly.
Yeah.
We're learning. We're learning.
Pettinelli on Facebook says, perhaps these questions are a little elementary, but how much of our understanding of black holes relies on our understanding of quantum physics? Are there minute values that influence the structure of black holes that we have identified?
I mean, in some sense, astrophysically, not at all.
Yeah, I mean, but black holes are typically classical kind of objects when you look at them from the outside. So unless we saw Hawking radiation, we wouldn't really be able to see those quantum fluctuations.
But there's a whole community of mathmaticians that are at their desks with pen and paper who are studying only the quantum aspects.
Yeah, only what
You'll find them in different buildings on a university campus.
All right. Viantus Zerulis, great name, on Facebook says, how useful would space-based radio telescopes be for taking black hole pictures?
Oh, they'd be fantastic. So it turns out that one of the big problems we have is the Earth's atmosphere. It's the water vapor in the atmosphere that's similar to what makes stars twinkle for optical telescopes that limits the Event Horizon Telescope. So if we could take a telescope and put it in orbit,
They're big,
we'd have a telescope as big as the orbital size of that.
How big is a radio telescope? How big across?
Well, the largest single one we use is about 50 meters across, 150 feet across. And then we have one in Chile that is
That'd be hard to get up in space.
All right. Mike Schneider's on Facebook says, if two black holes, one being a bit stronger than the other, were to meet, would they in theory cancel each other out?
They would just get bigger.
In fact, that just happened. LIGO made that first detection, and it's a
That's right.
wonderful and amazing result.
The first time in history we've seen two black holes collide, and what happens is they make a bigger black hole.
And some of the mass, though, is released as gravitational wave energy.
Thank you for the great questions in the lightning round, but sadly we're at the end of our time today. It's been a great day here at StarTalk All-Stars. Once again, thanks to Shep. If you want to hear more about Event Horizon Telescope, go to eventhorizontelscope.org and follow Matt on Twitter at Matt Kirshen, who is co-host of Probably Science Podcast, which is especially funny when I'm on it. And I'm Janna Levin. Thanks for listening. See you around the multiverse.
This is StarTalk.